Hello everyone, and thanks for joining us here at Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about Amperes Law. Our objectives are going to be to state and apply Amperes Law with symmetry arguments and the right-hand rule to relate magnetic field strength to current for planar or cylindrical symmetries, and apply the superposition principle to determine the magnetic field produced by combinations of Biot-Savart and Amperes Law configurations. So, let's start by talking about what Amperes Law is. This provides a much more elegant method of finding the magnetic field due to current flowing in a wire. The trick is you have to have situations of planar and cylindrical symmetry. And here's what Amperes Law says. The integral over a closed loop, note now this isn't a closed surface, it's a closed loop, of the magnetic field dotted with dl, that path you're taking in that loop, equals mu naught times the current that penetrates that loop. So lots of times I will write this as mu naught I pen for penetrating. As an example, let's draw a bit of wire coming out toward you. So there's our current. We could define some closed path, and we'll use symmetry. We'll make it a circular path in order to make it nice, simple, and symmetric, where our magnetic field, we can tell from the right-hand rule, is going to be in that direction. But we can define dl around that loop. The whole thing is done at some radius r from our Amperian loop, and then state that the integral over the closed loop, lots of times I will keep writing down here closed loop, of b dot dl equals mu naught I penetrating. B dot dl in this case, that's going to be b, and around that loop, that integral of the closed loop is going to be 2 pi r equals mu naught I. So you could go and say b equals mu naught I over 2 pi r, where I is penetrating, that is the current that penetrates that loop. Let's put it into practice a little bit more formally with the same basic example problem, but stated a little differently. Find the magnetic field outside a current-carrying wire. We did this with Biot-Savart, but oh my goodness, so much easier with Amperes Law. We'll draw our current. As we look at this end on, there it is, I. We have some radius of our wire itself. There's our wire with radius r. And we want to know what the magnetic field is at some point outside that. So we'll do that at some radius little r, and I'm going to draw our Amperian loop here in red. There it is. We'll call this little r. So that along our loop we have some small amount of that loop, dl, and we're going to have the magnetic field, B. If we want to know that magnetic field, we'll apply Amperes Law, integral over the closed loop of B dotted with dl equals mu naught times whatever current penetrates that loop. So the left-hand side is going to be B times the length around our entire loop, 2 pi r, equals mu naught. And the I that's penetrating our loop, well, it looks like all of this current I running in the wire is coming through is inside of our Amperian loop. So that's just going to be our total I, or like we said before, B equals mu naught I over 2 pi r. Nice and slick. But what if we want to look inside the wire? Now we want to know the magnetic field in here. Well, probably want to know that as a function of radius, so let's draw this again. I'm going to draw my wire first here in green. There it is with some radius, capital R. We know the current is coming out toward us, so I'm going to indicate that in blue. And we'll draw our Amperian loop now inside the wire. There we go, with some radius, little r. Now when we apply Amperes Law, the integral over the closed loop of B dot dl equals mu naught I penetrating. Now the left-hand side stays the same. That's going to be B times once around our Amperian loop, 2 pi r as we integrate that. The right-hand side, we still have mu naught, but how much current is actually penetrating? Well, if current is flowing through the entire wire, we need to know the amount that's actually flowing through this section over here. Well, that's going to be a ratio of their areas. So that's mu naught times, that'll be pi little r squared, the area of our Amperian, inside our Amperian loop, divided by the area of the entire wire, pi capital R squared. Times, of course, the current. So then, B equals, what do we have here? Mu naught, capital I, we'll still have a little r in the numerator, divided by, we have a 2 pi from the left-hand side, and we have an r squared left over from here. Mu naught IR over 2 pi capital R squared. So a linear function of radius while you're inside the wire. Let's take a look and see if we can't graph that to make some more sense of it. As we graph the magnetic field of a current-carrying wire as a function of the distance from the center of the wire, we'll start with our axes. So we have our magnetic field strength B, we have our radius r, and at some point here we're going to have our point capital R, right, when we go from inside the wire itself to outside the wire. And we just found that inside the wire we had a linear relationship looks kind of like that, where we said B was equal to mu naught I over 2 pi capital R squared times r, our radial distance. So it increases linearly until we get to the edge of the wire. Right at this point, we could plug in capital R for little r to find out that right here, our B is equal to mu naught I over 2 pi capital R. And from there, we have that inverse relationship where B equals mu naught I over 2 pi little r. So an inverse relationship with the distance from the center of the wire. So that's what that would look like as we combine it and put it all together. We can also use Ampere's law to find the magnetic field in a solenoid, a coil of wire. In this case, we're going to take a look at current flowing this way through the wire with multiple loops. We're going to make the assumption that the magnetic field is 0 outside the solenoid, a reasonable assumption. If we look at it in cross-section, you can see the current coming out up above and in down below. And I think that'll set us up, but what I'm going to do to help solve this is I'm just going to redraw our wire over here, and our choice of Amperian loop is probably a non-intuitive one unless you've done this a few times. So let's start by drawing our wire, our solenoid I should say, coil of wire, and we'll define the entire length of our wire as capital L. And my Amperian loop that I'm going to draw is going to be a rectangle that is partially in and partially outside that solenoid. I'm going to define the width of my Amperian loop as little l. Now as I look at this, we've got some nice things going on here. Outside the solenoid, the magnetic field is 0, so we don't have to worry about this part. And let me number these sides. 1, 2, 3, and 4. 2 doesn't have any magnetic field that we have to worry about. 1 and 3 are parallel to the current, so we're not going to have any effect there. We really only have to worry about this section 4 when we do our closed loop. So let's apply Ampere's law. The integral around the closed loop of B dot dl equals mu naught times I penetrating that loop. Which implies then, since I penetrating, well, how much current is penetrating that loop? Well, we've got the ratio of this length to the total length, L over L, times the total number of loops, capital N. So L over L, little l over big L, times capital N tells you the number of loops that are penetrating our Amperian loop. And then we have to multiply that by the current that's in it each time, so that'll be times capital I. So every time it goes through, we count that as penetrating our loop once. So once we do that, we can take a look, and our closed loop, since we're only worried about section 4, 1, 2, and 3 have no contributions, we have B times little l, the length of our section 4 of our wire, must equal mu naught times I penetrating, which we said was L over capital L, the number of loops N, times I, or B equals capital N over L mu naught I. Nice slick application of Ampere's law. All right, let's get a couple more of these force magnetism type examples before we get into a couple AP problems to finish out our discussion of Ampere's law. So, rectangular wire loop carrying current I lies a distance r to the right of a long wire carrying current I2. What is the direction of the net force on the loop? Well, the first thing I'm going to do, if I want to know the net force on this loop, is I'm going to find the magnetic field due to I2 that's going to affect it. So if I2 is traveling up the screen, that means using the right-hand rule, our magnetic field over here is going to be in to the plane of the page. So knowing that, I'm then going to look at these different sections and see what we get for a force with each section. As I look over here on the right-hand section, we have positive current traveling up the screen. Bend the fingers of your right hand 90 degrees in the direction of the magnetic field into the plane of the screen, and I come up with the force here to the left. At the top, as the current is traveling to the left of the screen, I get a force down. To the bottom, as the current is traveling to the right, I get a force up. And these should be balanced because they're symmetric. And in this section, as the current travels down, I get a force to the right. However, as I look at this, we have the strongest force over here because we're closest to the wire. We've got the strongest magnetic field. Therefore, we should draw that arrow a little bit bigger than that arrow, and I would say that the net force then must be to the right. Yeah, let's see. Rectangular wire loop carrying current I lies a distance r to the right. The long wire carrying, what is the direction of the net force on the loop? Yeah, very good. All right, let's take a look at a couple of AP problems. We're going to start with a question from the 2011 E&M exam, free response number 3. So take a minute, go find that, Google it, go to the address here, print it out, try it for a couple minutes, pause it, come back, and we can either check them, or if you got stuck, see how we can get you past that point where you got stuck as we go through it. So let me pull that out. And in 2011 E&M question 3, we have a long conducting cylinder with an inner radius A, outer radius B, carrying a current I naught that has a uniform current density, which they show you. Using Ampere's law, find the magnitude of the magnetic field in those regions. Well, let's start with region 1. We'll use Ampere's law, integral over the closed loop of B dot dl equals mu naught I penetrating. But because we are inside that entire thing, there's no penetrating current. If there's no penetrating current, then our magnetic field must be 0 for r inside that, for r less than a. For part 2, this is when we're actually inside that wire, or inside that cylinder. So integral over the closed loop of B dot dl equals mu naught I penetrating, and I should mark here closed loop. So the left-hand side, of course, is going to be B times 2 pi r, our distance as we integrate around our closed Amperian loop, 2 pi r, equals mu naught I penetrating. But I penetrating is a little tricky here. We have mu naught, and to get the amount that's penetrating, well, let's take the entire current. But how much is actually penetrating our entire loop? Well, that's going to be the ratio of the areas of our cylinder, which is going to be pi r squared minus pi a squared in the numerator, and we have to divide that by the current to get our current density of pi b squared minus pi a squared. So there's our penetrating current. So then to solve for B equals mu naught I naught, what do we have here, over 2 pi r times the quantity, and we can factor out our pi's here, of r squared minus a squared over b squared minus a squared. All right, so there's our magnetic field for part 2 inside that cylinder. And for part 3, let's take a look here. When we're at 2b, well, the integral over the closed loop of B dot dl is equal to mu naught I penetrating. In this case, our r equals 2b. So the left-hand side, b times 2 pi, our r again is 2b, equals mu naught, and the current that's penetrating that is that entire current, I naught. Therefore, b equals mu naught I naught over 4 pi little b. All right, good start here. Let's move on to part D, where it says now we're considering a long solid conducting cylinder. I'll move to the next page to give us some room here. And it tells us the magnitude of the magnetic field is given by that function. An experiment is conducted in which we're measuring the magnetic field as a function of r, and that data is tabulated. It asks us to graph that question then. So, oh, hang on, I think I skipped part B. Yeah, we got to go to part B first. We got a cross-sectional view. All right, on that cross-sectional view, we need to indicate the direction of the field at point P. Oh, well, that's easy. There we go. At point P, if we have current coming out of here by the right-hand rule, that's just going to be perpendicular to that radius, so there's B. And at point C, an electron is at rest at point P. Describe any electromagnetic forces acting on the electron. Well, let's see. The electric force is Q times the electric field. There is no electric field, so there's no electric force. And we have the magnetic force equals Q V cross B. And V equals 0, therefore there's no magnetic force. So there are no electromagnetic forces on it. All right, now let's go to part D in our graph. Let's give ourselves a little bit more room here again, too. Drawing our graph. Would label it something like our magnetic field strength in Tesla versus our distance in meters. And I'll let you pick the points, but I use something like 2 times 10 to the minus 4, all the way up to 6 times 10 to the minus 4, and here we went 0.002, 0.004, and so on, all the way until you get to about 0.01. Plot your points, you draw your best fit line, you get something that hopefully looks fairly linear. All right, so once you've done that, use the slope of your line to estimate a value of the permeability mu naught. Well, slope is rise over run. So pick 2 points on the line, not data points, to calculate your slope. Make sure you're careful with your units. And I ended up with something around 0.0635 Tesla per meter for my slope. But then how do we use that to find permeability? Well, we have our equation B equals mu naught I naught over 2 pi b squared times r. Fitting this to the form of a line, y equals mx, our slope should be mu naught I naught over 2 pi b squared. Therefore, if we wanted to just find mu naught, well, slope equals mu naught I naught over 2 pi b squared. Let's change up our color a little bit, which implies then that mu naught equals 2 pi b squared over I naught times our slope. So now we can plug in our values. Mu naught equals 2 pi times 0.01 meters squared divided by our I naught, which was 25 amps, times our slope, 0.0635 Tesla per meter. And I get about 1.6 times 10 to the minus 6 Tesla meter per amp, which is reasonably close to 4 pi times 10 to the minus 7, which is about 1.26 times 10 to the minus 6. So we're at least in the ballpark there. Okay, so that's the 2011 question. Let's take a look at the 2005 exam, free response number 3. Take a minute, go download it, print it out, pause the video for a second, give it a try, and come back here when you've had a chance to look at it. And it starts out, we have this experiment, what I do in my classroom all the time, where we've got a slinky, we're putting some current through it, with a variable voltage supply, measuring the current, and we use a Hall probe, which is a tool that helps you measure a magnetic field at a point. So what it's going to have you do for part A is fill in n, the number of turns per meter. And for the first one, for example, when you're at 40 centimeters, the turns per meter, well, if you have 100 total turns, divided by 0.4 meters, that's 250 turns per meter. And you just keep filling that out for the 5 different trials to get your data points. Then for part B, what we're going to do is plot the magnetic field versus n, your turns per meter. And when I do a plot like that, let's see, should get a graph that looks roughly linear. And I ended up with points when I drew my best fit line somewhere over there in my graph if I used it carefully. Plot the points, draw your best fit line. And then for C, it's going to say, obtain the value of permeability using that graph. All right, well, as we look at what we have there for B, we're going to have to move on. Let's give ourselves a little bit more room for our calculations here. So for part C, B equals mu naught n times our current. Therefore, mu naught equals B over n I, which is going to be the slope divided by the current. Then we can find our slope using points on the line, not data points. Rise over run. I came up with something around 3.81 times 10 to the minus 6 Tesla meter per turn. And if mu naught equals slope over I, well, Let's use that. Mu naught equals slope over our current, which would be our 3.81 times 10 to the minus 6 divided by our current 3 amps, or about 1.27 times 10 to the minus 6 Tesla meters per amp. Which, as we just mentioned, is awfully close to 4 pi times 10 to the minus 7, the accepted value, which is 1.26 times 10 to the minus 6. So for part D, it says, using that theoretical value, determine the percent error in the experimental value computed in part C. Well, our percent error is the absolute value of our actual result minus the accepted value, 4 pi times 10 to the minus 7, all divided by the accepted, times 100%, which will be, well, if we want the absolute value, and this one's bigger, we're going to have our 4 pi times 10 to the minus 7 minus our 1.27 times 10 to the minus 6. I think I did that in the reverse order, but it's absolute value. It'll work out just fine. Over our 4 pi times 10 to the minus 7 times 100%, which gives you 1.06%. Pretty good, and a fun experiment to actually try because it usually works out very well. All right, thank you for watching Educator.com. We'll see you again soon. Make it a great day, everybody.